In part two of my conversation with Environment Canada climate scientist Greg Flatto, we discussed the dynamics of CO2 in the troposphere, the tropopause, and the stratosphere. Carbon in one layer of the atmosphere has a completely different effect on the admission and containment of heat from the sun than in the other. We dig into the various greenhouse gases. For example, did you know that by far and away water vapor is number one, followed by CO2 and methane or natural gas? We also discussed the fascinating makeup of methane or natural gas, which has been labeled as the cleaner greenhouse gas. But it turns out that isn't true. In fact, natural gas is 20 times more effective than CO2 as a greenhouse gas. The saving grace is that there is considerably less methane than CO2 being used to produce energy. Most importantly, this conversation concludes on a positive note. Mr. Flatto, like climate scientist Simon Donner, is optimistic that collectively we will find solutions to the climate challenges we face. Here now is part two of my conversation that matters with Environment Canada scientist Greg Flatto.
Conversations That Matter is a partner program of the Centre for Dialogue at Simon Fraser University. The production of this program is made possible thanks to the following and viewers like you. Please become a patron at conversationsthatmatter.tv.
I'd also like to get you to explain what the different layers of the atmosphere are, because I know we live in the troposphere, and then there's the tropopause and the stratosphere, which is where I understand that, for the most part, and tell me if I'm wrong once again, that when we emit carbon out into the atmosphere, that's in essence where it's going. But does it then also move into the mesosphere and the thermosphere and so on? And so what is the impact across all of those different layers of atmosphere that surround the Earth?
Okay, so you're very well informed about the vertical structure of the atmosphere. There's probably not many people who could name all the layers.
Well, I'm fascinated by it because I want to know, and there from my perspective, there's so many people who throw things out, but they're not really talking about it from even understanding what the components are. So I'd like to understand those layers, and then say, okay, well, as you pointed out, water vapor is the largest portion of greenhouse gas, but I actually would like to drill down and understand a little bit of those too. But first, let's talk about the layers of the atmosphere, and then talk about what are those different greenhouse gases, because I think that interplay, and if we understand that, then we can understand what our relationship as human beings and our activities, how it affects that. Because I've been searching for this information, and so much of it is clouded with other agendas. I want just, to understand, well, just the facts, ma'am.
I'll give you the facts. So, yeah. the troposphere is the lowermost layer of the atmosphere. Its thickness is a few miles. So where you fly in a jet airliner is somewhere near the tropopause or into the very lowest stratosphere. So it's that lower part of the atmosphere. It's called the troposphere because it's some Latin derivative, but it means it's well mixed, basically. So that the troposphere is where all the mixing happens, because we have areas where the surface heats up. You get convection, you get these clouds, you have there's lots of turbulence and lots of mixing in the troposphere. So when we emit carbon dioxide from our cars, from industrial processes, from whatever those emission sources are, agricultural practices, forest fires, whatever it is, they get emitted into the troposphere because that's where they're emitted. They get mixed around in there. Then you have the tropopause, which is the top of the troposphere, and then the stratosphere above it. The stratosphere gets its name from strata, which is layers. So the stratosphere is a layered system. It doesn't mix vertically as much. It's very what's the word I'm looking for here? It's always hard when you haven't had your coffee in the afternoon.
Static or so in its structure?
Very stratified, so that the layers don't mix one with another. So there's the carbon dioxide, for example, gets well mixed in the troposphere. Pretty much everywhere you measure it, you get nearly the same number. It's not exactly the same number because it depends on if you measure in the northern hemisphere or the southern hemisphere, the seasonal cycle of the vegetation is out of phase, and so you get a difference. It's very well mixed. When you get into the stratosphere, some of it mixes across the tropopause into the stratosphere, where it very slowly mixes into the stratosphere. So some of the carbon dioxide we emit does get into the stratosphere. And it's a greenhouse gas in the stratosphere just as it is in the troposphere. The other thing that not we put in, but that nature puts into the stratosphere is explosive volcanic emissions. So when a big volcano emits something, so you think about Pinatubo, for example, it's a very explosive volcano that ejects very energetically material through the troposphere up into the stratosphere. It puts ash, and it also puts sulfur, and the sulfur combines with water to produce sulfur dioxide. The sulfur dioxide little droplets are very reflective of solar radiation, as is the ash, and they have to cool a climate by reflecting solar radiation away. So I think about putting little umbrellas up there. The effect of a greenhouse gas in the stratosphere is actually, if you put this, the same molecule of carbon dioxide in the stratosphere versus in the troposphere, it will warm the troposphere and cool the stratosphere. So you get this different behavior, and that becomes important for approaches to measuring temperature from satellites. The way that satellites measure temperature is they measure the radiation coming from the surface in different frequency bands, and they can ascribe those different frequency bands to different elevations in the atmosphere.
I got to get you to hang on for a second while we take a quick commercial break. We'll be right back. Conversations That Matter is brought to you by Odlum Brown, a client-focused investment firm that starts client relationships with straightforward conversations focused on you, your aspirations, and your investment priorities. Odlum Brown has been a supporter of Conversations That Matter from the day we started this show. Their only condition was that we provide a non-biased conversation with people from all sides of all sorts of issues. And of course, we couldn't produce this show without the support of Oh Boy Productions. If you're looking to produce a show like this one, I suggest you reach out to Oh Boy. They can help you produce it, and they can help you build your audience. And we also need your support. I ask you to please pledge $1 per show by going to conversationsthatmatter.tv/donate, because those dollars add up and play an important role in helping us produce this show. Now, back to the show. So
I don't know if that helped at all, or if that
it helps a lot, but it leaves me, of course, with more questions. So if that's happening in the troposphere and the stratosphere, is there an impact from human activity that even radiates out into the mesosphere? Or do we sort of see, because you indicated that it's through the explosive nature of a volcanic eruption that carbon and ash winds up in the stratosphere. Is that about as far as it's going? And so the most important areas for us to concentrate on are the stratosphere and in particular on the troposphere.
Yeah. The other reason that it's important to think about the stratosphere is for ozone depleting substances. So when you put chlorofluorocarbons, other substances, most of which are controlled under the Montreal Protocol, what was discovered back in the 70s is those ozone depleting substances get up into the stratosphere. They have a very long lifetime up there. They're involved in some catalytic chemistry that destroys or breaks down the ozone that is in the stratosphere. That ozone that's in the stratosphere is very important for human health, for ecosystem health, because it reflects ultraviolet radiation back into space. It's the little umbrellas that protect us from UV radiation. So that ozone layer in the stratosphere is very important for a number of reasons. And so the control of these ozone depleting substances that were creating these, the ozone holes in the polar regions was important. So that's another reason why understanding what's happening in the stratosphere is important. And there's a connection between the climate change and ozone chemistry, because that ozone chemistry is temperature dependent. So as you make the stratosphere colder, the chemistry that is involved in ozone depletion changes.
So I'm somewhat encouraged when you talk about the Montreal Protocol, because there was, for the most part, a global response to that. And it's my understanding that our reaction is having a positive effect on the ozone regenerating and putting that protective layer back in place. And if we were able to do that, then does that provide us with encouragement with regards to other aspects of the way in which we affect climate?
Well, I think it does. And so you're absolutely right. It is the case that we can now see that the ozone depletion has stopped and it's starting to recover. You can start to see the ozone level starting to come back up again. And there's some recent papers that analyze that and look at what is the human contribution to having turned that around. So that is one good example. There's another good example, which is the acid rain example. So back in the 70s and 80s, acid rain was a big problem, and it was a result of burning coals that have high sulfur content. That sulfur gets into the atmosphere, and just like for the volcanic emissions, it produces sulfur dioxide and combines with water, produces these little aerosols, little tiny droplets that reflect solar radiation back to space. They have a cooling effect on climate. But they also have an effect when they wash out of the atmosphere because they produce more acidic rain that impacts plants. It leads to acidification of lakes and streams and so on, and lots of harmful environmental effects. That was very well recognized. And so regulations to control emissions from coal and oil burning power plants were introduced. And we've, in Europe and North America, really successfully eliminated that problem. So there are good examples of actions that have been taken by society, by governments, through regulation or otherwise, to affect change that has had a positive environmental effect. That is to turn around something that was negative. The difficulty is that in both of those cases, the sources are pretty specific and pretty localized.
Well, Patrick Flannery, who had been the climate commissioner in Australia, I had him as a guest on the show, and he said that the number one source of carbon that is emitted into the atmosphere comes from the burning of coal to generate electricity, primarily in India and China. And so this makes our challenge very, very difficult, if that's correct, because how do we collectively say, well, you can't do that? Now, maybe we can look at, efforts to try and replace that with a cleaner burning fuel as being a good step forward. But is he right about that fact that it's the burning of coal that is the number one source of carbon that's being emitted into the atmosphere?
I don't have the statistics in front of me, but if it's not the number one, it's in the top one. I mean, basically, the combustion of fossil fuels altogether is the number one thing, is the number one source of carbon dioxide emissions into the atmosphere. So yes, those are the things that have to be the target of emission reduction efforts if we want to reduce those emissions. And it is true that the growth has primarily been in India and China. In North America and Europe, our emissions, our fossil fuel emissions, have either plateaued or begun to decline.
That's good news.
It is good news. The growth has been in other countries.
What are the greenhouse gases that are that exist? I know of water vapor, methane, and carbon. What are they, and what in relationship are they in percentage of overall greenhouse gases?
Water vapor is far and away the largest greenhouse gas. Carbon dioxide is next. And so people talk about carbon and carbon dioxide. The carbon that's in carbon dioxide or the carbon that's in methane, which is CH4, it's carbon. It's basically an accounting issue of how you count the amount of carbon dioxide. You can either measure it as kilograms or kilotons or gigatons of carbon dioxide, or you can measure it in terms of just the carbon content of it. And often it's just measured in terms of the carbon content of it so that it's easier to compare with the carbon content of the fuels that were used to produce it. So methane is the
carbon.
The chemical number or the chemical formula for it is CH4. So it's carbon with 4 hydrogens Carbon dioxide is carbon with two oxygens. They both have carbon in them. Methane is released through a lot of the same processes from which we get petroleum products. So it escapes from processing of natural gas. Methane is basically what you call natural gas, but there's lots of natural sources for it. So decomposition of organic matter produces methane if it's in a wet environment. It produces carbon dioxide if it's in a dry environment. So, but methane has an important property in that it is about 20 times more effective as a greenhouse gas than carbon dioxide. So one molecule of methane in the atmosphere has the same warming effect as 20 molecules of carbon dioxide. And that has to do with the way they absorb and re-emit. It has to do with the way that radiative transfer in the atmosphere works. So methane, although it's a much smaller in percentage terms, it has a disproportionate effect.
So it's not any greener than CO2.
In terms of when it's in the atmosphere, no.
Okay, that's an interesting thing, because I keep hearing that people go, oh no, it's a cleaner fuel.
Well, yeah, and so again, you have to be clear on what we're talking about. So in terms of comparing, say, natural gas to coal, it's cleaner in the sense that you get more energy per amount of emissions that you produce. And that has to do with the molecular structure of coal versus methane. So it's cleaner in that sense. It's a relatively small ratio, but the energy that you get for the same amount of ultimate carbon dioxide that you put in the atmosphere is a bit higher for natural gas than it is for coal, because you have to use some energy to break the coal down into things that will ultimately volatile. Nitrous oxide is the next big one. That mainly is a result of agricultural practices. So fertilizers that are used in modern agriculture, that's a big source of that. Some other industrial processes. And then there's a bunch of small ones, and a whole range of chlorofluorocarbons, those ozone depleting substances. They are also greenhouse gases, and very powerful greenhouse gases when they're in the troposphere. So there's a bunch of them. So they have a double whammy role. They both have a warming effect and an ozone depleting effect.
So with all you know about this, are you worried about the future? Or do you think that we have the collective capability to address this issue? Because I don't foresee us really moving away from the use of energy to make our lives simpler, easier, more productive, and all of these things. This is going to be a very hard habit for us to wean ourselves off of without having an appropriate replacement. And so I'm asking, are you hopeful that we can get there and do so in time?
Well, I'm an optimistic person by nature.
I can see that.
The way that you explained it was actually very effective, because we do have a very energy intensive way of life, a very energy intensive society. Our transportation system, the fact that we're talking back and forth to each other on computers that use energy through a network that requires energy, in an office that has lights that require energy. So energy is an essential part of kind of modern life. The big issue is, where do we get that energy from? And we can get it from renewable sources, or we can get it from sources that continue to put carbon dioxide and other greenhouse gases into the atmosphere. That's the fundamental choice, is how do you maintain a supply of energy that is necessary for society to function on, and do that by transforming away from a fossil fuel-based energy source to a renewable energy source. And so we have the capability to do that. We have the technology to do that. We have, hydropower in British Columbia, for example, produces most of our electricity. So that's already a good thing. In many places, solar power and wind power are becoming increasingly deployed, and the cost of deploying that is getting smaller and smaller. There's lots of work on smaller scale hydroelectric things, run of the river type systems, other small hydro distributed sort of systems that would provide energy, work on tidal and wave energy, geothermal energy, lots of other sources that are being looked at. Now, not everything can be run on electricity. You can't have an electric airliner.
Not yet, anyway.
There's still a need for other forms of energy, but there's also alternatives there. We have lots of liquid fuels that can be produced from agricultural products. We have biofuels and biodiesel and ethanol. Those are all things that also are available and are renewable. We have technologies to produce electricity using bioenergy with carbon capture and storage, which actually is a net removal of carbon dioxide from the atmosphere, which is a positive, gets you a 2-for-1. So there's lots of available technology. I think it's the willingness to change the way that we do things, changing the kind of vehicles that we buy, making sure that we're doing things in an energy efficient way, being more conscious of not using energy, not wasting energy when we don't have to. I mean, the simple things like turning your lights off and using cold water to wash and or wash your laundry and things. All of those things save energy, and the energy that you save ultimately translates into a reduction of emissions.
And that's a really good point to make, that we all play a role in this. It's not just government and industry that can solve this. We all have a part to play in this, don't we?
Absolutely. It's at all levels, from the individual to the international. We all play a role, and we all make decisions every day that we that have an influence. Just turning the light off when you don't need it, not taking a trip to the store to get one bottle of milk if you don't really need it, and you can save it until grocery day on Saturday. All of those things that are pretty small, common sense things that I think are don't really have a big negative effect on our lives, but do add up. And I think that it's all of those things together, along with the technologies that are available to provide alternative sorts of energy, that I think that's what keeps me optimistic that we are going to do something. Maybe not as fast as many would like, but I'm optimistic that it's clear enough to most people that we are having an effect on the climate. Humans are changing the climate, that if we don't make a change in our behaviors, our lifestyle, our energy usage, our energy sources, that will just continue to get worse. And that has an effect that is even more profound on the poorest people in the world.
That's a great place for us to end. Thank you very much.